Okay, we may start. Do you hear me?
Yes.
Yes. Okay, great. Then today's talk by Zhuoke Yang will be devoted to new approaches to GLN weight systems. And there are it's a difficult point how to write it, weight system or weight systems. On one hand, such a weight system depends on n. On the other hand, it is universal and one and the same for all n's. So we will see during the talk. You may start, Jackie.
So my talk title is New Approach to the GLN weight system. First of all, it's a Chord diagram. It's just an orientated loop and several chords. And next is four-term relationship. It says like this.
So, as usual, we are interested in weight systems, which are functions on chord diagrams satisfying these four-term relations. For arbitrary chord diagrams and arbitrary pair of chords with neighboring ends.
Yeah, it's for a chord diagram, and there are two chords A and B. This is the first and the next. You switch the endpoint of the A and B. I call this chord diagram is DAB. AB is just selected the chord, and this is DAB prime. This is AB tiered, which you switch the endpoint of chord A to another side of the endpoint of the chord B. And this is you cause this to endpoint. I call it DAB tiered prime. And
Please address the audience rather than the blackboard.
I see. So next, the weight system. Weight system is a function f on the chord diagram. And a satisfied four-term relationship, which is df minus dr2. Well, this is a weight system, definition of the weight system. And next, we focus on the Lie algebra weight system. And we say that G is a metrized Lie algebra. And they have the AD invariant, non-degenerated. Bilinear form. And we say that the D is the dimension of G. And we need to choose a base of this Lie algebra G. I call it E1, E2, ED. The base of the Lie algebra G. And since we have this bilinear form and the base, we have the dual base. E1 star, E2 star, ED star. Is the dual base.
Коллеги, которые в Zoom присутствуют, вы отключите, пожалуйста, звук у себя, если вы не задаете вопросы, а то какие-то посторонние звуки. There are some auxiliary sounds from Zoom participants.
And I said dual base, which means that EI, EJ star equal to delta IJ, which means only equal to 1 when I equal to Z, otherwise it's 0. And I show you the definition of the Lie algebra wave system.
So, please write down that both EIs and EI stars, EJ stars are elements of G.
Sorry, where?
EI, all the EIs are elements of G. Yeah?
Yeah, it's a base of the G.
Yeah, and all the EI stars also are elements of G.
So.
Just write that they belong to G. Yeah.
And so for arbitrary chord diagram, and what you need to do is find the arbitrary chord point, cut point. Cut point. And
Could you please use larger letters?
Okay.
Like twice or 3 times.
And since we have orientation of this loop, and you follow this loop, and so maybe I give name of all the chord. So we have the chord A, chord B, chord C, and there.
Larger letters, please.
Larger letter, yes.
I mean, for online listeners, it's just
maybe we draw a bigger chord diagram. So I call this chord A, chord B, and chord C. Orientation, and there you just label all the endpoint of the chord. So this one is IA. Oh, sorry. I use when you first time meet the endpoint of chord, use the EIA, and this is EIB. And next time you meet the endpoint of the same chord the second time, use the base in the dual. Use the dual base. So EIA, EIB, EIA star. This is the first time you meet the chord C, so EIC. This is EIB star, and this is EIC star. And now we can write this wave system of the Lie algebra G of this chord diagram D. And you product from the loop, product everything from the loop. So EIA, EIB, EIA star, EIC, EIB star, EIC star. and you sum up for all the index from 1 to D. And so this is the definition of the, maybe I don't need this number. So this is the definition of the Lie algebra weight system, and we claim something. First is this the G weight system. So this WG is not dependent the cut point. And second, it's not dependent on how you choose the base.
And please write down that this element is an element of the universal enveloping algebra of G.
Yes, So
it belongs to U of G. Yeah.
U of G. So it's not it's the product in the universal. Yes, yes. And
to the center.
Yes. So weight system is not belong to the only belong to the universal enveloping algebra. It's also belong to the center of the universal enveloping algebra.
And it satisfies the four-term relation. It is indeed a weight system.
Yes, it's indeed it's a weight system, which means that the WD is satisfied. Four-term relation.
So this construction is very universal. It can be applied to arbitrary Lie algebra endowed with a non-degenerate bilinear ad-invariant form, and it indeed can be applied to such a Lie algebra. But the general problem is that in spite of this very simple definition, the computation of this weight system is extremely complicated already in the case of simplest Lie algebras like SL2, as probably Polina is not here. We have at least a number of people were trying to compute the values of these weight systems in the simplest case. However, it's extremely difficult, and what Zhuoke is going to talk about is a serious progress in computing this weight system for a specific series of Lie algebras, namely for GLN. Значит, определение само по себе очень простое. Оно, вы берете алгебру Lie с невырожденным инвариантным скалярным произведением, берете в ней какой-то базис, и по этому базису строите значение весовой системы WG на любой хордовой диаграмме. Проблема в том, что определить-то вы определили, но вычислить то, что получится, крайне сложно. И только в простейших случаях, например, в случае алгебры Lie SL2, можно получить какие-то явные результаты для достаточно больших хордовых диаграмм. И вот то, что мы обсуждали у нас на семинаре в начале этого года в том числе, а то, о чем сейчас будет говорить Zhuoke, это очень серьезный прогресс в понимании весовых систем, связанных с алгебрами Lie GLN. целая бесконечная серия алгебр. Эти весовые системы отвечают тому, что называется тому, что называется многочлен Хомфли ПТ. Вот. И они, инварианты узлов многочлена Хомфли, они играют ключевую роль вообще в том, что можно вычислить, и до сих пор ничего про них не было понятно, а вот сейчас очень многие вещи удается посчитать. Окей. Значит, весовая система – это функция на хордовых диаграммах, удовлетворяющая четырехчленным соотношением. Вот эта вот функция, она принимает значение в центре универсальной обертывающей алгебры, алгебры Лиже. Этот центр – это коммутативная алгебра, и там понятно, что означает, что функция удовлетворяет четырехчленным соотношением. Well, continue, please.
So, GLN weight system. So, first the Lie algebra GLN, and we can think this is order n time n matrix, and we can choose the bilinear form. It's just
larger letters, please. Otherwise, people are unable. Значит, алгебра Лиже-Лен это тоже простейшее, что бывает. Вы берете n на n матрицы. И скобка Ли это для пары матрицы АБ, это АБ минус БА. Обычная скобка Ли. А вот скалярное произведение, the scalar product is just the trace of the product of two matrices, X and Y.
Product as matrix. And the base, it has a natural way to choose the base is the EIJ. Is the base of the Lie algebra GLN, and the dual base.
You has not told us what are EIJ.
Oh, okay. So EIJ is the matrix whose have 1 at the isomorphism and the J is colon in there, 0 otherwise.
EIJ are matrix units. Значит, матрица E с индексом EIJ имеет... Это такая матрица, у которой единица на пересечении итой строки и житого столбца и нули во всех остальных строчках, во всех остальных клетках. EIJ has 1 on the intersection of i's row and j's column, and zeros everywhere else. Sorry? Transvection. Don't know. Matrix unit. Transvection is a different.
And also that in this case, the dual base. It's EIJ star, which
we will ask the audience, what is EIJ star?
Транспонированная единичная матрица.
I was asking students rather than you, Misha. Yeah.
I just knew the answer. So just
yeah, J star is just
the EJI.
EJI. Значит, если вы матрицу E и G умножите на матрицу E, G, E, то вы получите матрицу, у которой на диагонали стоит единица в этой позиции. Ее след равен единице. Поэтому это действительно двойственный бейс. Окей.
And also that in the GLN we have the Lie bucket, and it's on the base. It's look like EIJ, EKL. It's Eij EKL minus EKL Eij equal to delta JK EIL minus delta IL EKJ. So this is a bucket, which is a commutation in the GRN.
Will you please write down WGL of D for this diagram D you have placed here?
You mean
Mm-hmm.
calculate this? Oh,
Yeah, for this specific diagram.
okay. But this is a little bit, maybe with more simple, maybe just only 2 chord.
But you may write.
Oh, you mean
the
just
same,
the
yeah,
oh,
just the
okay.
same expression.
Uh-huh.
I'm not asking about the result.
I see. So that,
Just right here.
Oh, right here, okay.
You have enough place here.
Uh-huh.
Yeah.
So the wave system GRN of this chord diagram D. So we still have the.
Just write down. Don't make. Correction.
So
yeah. Nope.
Eij.
Nope.
No, like this.
You have to have big E's.
Yes.
Capital E's rather than.
Eij.
Mm-hmm.
EKL EJI, which is EIJ starts EJI, and here is EMN ELK ENM.
Mm-hmm. And
So
IJK.
IJKLMN from 1 to
N.
N.
And also, please write down the dimension of GLN.
Dimensional is
D is equals to
N square. The dimension.
D equal to N square.
D equal
Sorry,
to
but
dimensional D is equal to N square.
Mm-hmm.
And the Casimir element in the GRN. So the simplest chord diagram you can take like this case, which is a loop with exactly 1 chord. And then for the definition, it's summation of Eij, Eji, Ij from 1 to N. And this is actually we call the C2. The second Casimir element in the GRN. And the Casimir element is actually, you can say it's a base of the center of the universal enveloping algebra of GLN. It's a polynomial. So we have the JU GLN is isomorphism to the polynomial C1, C2, Cn. And C1 equal to summation EII. I from 1 to N. C2 is the summation. And I write for general CK. Summation EI1, I2, EI2, I3, EIK minus 1, EIK, IK, I1. And I1, IK from 1 to N.
Great. Значит, центр универсальной обертывающей алгебры Ли GLN очень легко описать. Это кольцо многочленов. Ну, тут написано над полем К. Ну, можно считать, что над полем комплексных чисел. if you write down please that k is equal to c, our ground field will, we may suppose that it is the field of complex numbers, yeah?
Yeah, field is
Yeah.
complex number or real numbers, quite not big.
Значит, это кольцо многочленов от n переменных, c1, c2, cn. Ну и эти n переменных, это не просто какие-то n переменных, а это, во-первых, они градуированы в том смысле, что c1 это элемент алгебры Ли, c2 это элемент квадрата, тензорного квадрата этой алгебры Ли, c3 это элемент тензорного куба и так далее. Они градуированы. Фильтрованы, если уж быть точнее, да, но там в универсальной обертывающей алгебре есть фильтрация и нет градуировки. И, ну, это некоторые вполне конкретные n элементов, и, то есть значения весовой системы GLN, которые будут получаться на хордовых диаграммах, это будут некоторые многочлены от вот этих вполне конкретных n элементов. The value of the weight system GLN on a chord diagram is a polynomial in these n elements, C1, C2, Cn.
And now I can show you an example like how to exactly calculate for a specific chord diagram. For example, like this. This is a chord diagram, and we're trying to calculate the GLN weight system of this chord diagram by following the definition. GLN. So they have the 4 endpoints, so EIJ, EKL, EJI, ELK, IJKL from 1 to n. And our goal is to transform this form into the Casimir element. So now we switch these two places by this relation. JKL 1 to n IJ, and this is ELK. So KL JI, it's EKL, EJI, and plus EJI, EKL. And JKL from 1 to n. And this is actually the delta LJEKI and minus delta IK EJL. So that's totally 4 terms. So first one is EIJ delta JL EIJ EKI ELK minus IJKL дельта.
Дельта ежи здесь это кронекеровская дельта, которая равна единице, если индексы совпадают, и нулю, если индексы различны. Да. Ну, я про это сказал. What I've told is that the Casimir element CK is of gradient K, which is not true in fact, because there is no gradient in the universal enveloping algebra. There is only filtration, so that we have an increasing sequence of subspaces in the center of the universal enveloping algebra, and Ck belongs to the case element of this filtration. Ну вот у вас квадратичный элемент, он не квадратичный на самом деле, он квадратичный с точностью до линейных членов. Потому что коммутатор двух элементов нашей алгебры Ли — это элемент алгебры Ли. Поэтому нельзя сказать, что там есть чисто квадратичный элемент. Мы их можем коммутировать и добавлять к ним элементы первой степени. Но тут то же самое, что нельзя говорить про кубическую часть чисто. Там есть элементы степени не выше 3. Максимальная, да. Но может быть.
And there, so we just write this index, the delta JL, which means L is just a J. There's no L. And in this case, we have the delta IK, which means I equal to K. K is become 2 I. Sorry. IJ, this is the K, JK. This is JL. JL, LK, so K is I, so L is I. And there's no K. And you compare this to this is EIJ. EIJ, this is KI, JK, you get the JLLI. You can rewrite this L to K. And then this two you can compare as Lie buckets. So we got the EIJ, EKI, EJK. And you know that you can notice that the last term is exactly the C2 square. So it's IJJI, KLK, so it's C2 square. And for this, you get the delta IJ EKK minus delta KK, which is 1 EJI. So first EIJ times delta IJ EKK, which is EII times EKK, so it's C1 square minus IJ, so that's delta KK. So is there still sum for the K, so minus N times C2. This is IJJI, so minus C2 square. So this is the final result for the.
There should be plus. The last sign is plus,
yes,
rather than minus.
Plus.
So in principle, the same thing can be done for arbitrary Chord diagram. But the computations become more and more complicated, and already for diagrams with 4 or 5 chords, it is very difficult to obtain a final answer. And here we have only 2 chords. And that's a general problem when making computations in non-commutative algebra. The universal enveloping algebra of the Lie algebra is non-commutative. And in spite of the fact that the final result belongs to a commutative algebra, the center of the universal enveloping algebra, intermediate calculations, all intermediate calculations are to be made in a non-commutative algebra, which makes them extremely complicated and extremely inefficient. And now Zhuoke is going to tell us how this difficulty can be overcome in the case of GLN.
first of all, I need a new definition called the permutation weight system, GRN weight system. For permutation. So we have a permutation sigma belong to Sm, and we write the, and we will assume that the sigma don't have the fixed point, no fixed point.
You don't need that.
Actually, it's if you assume that there are no fixed point, it would be more convenient to write this GRN weight system of this sigma.
Do you really need? There is no need for definition, at least.
Okay. So the definition is EI1, EI sigma 1, EI2, I sigma 2, EIM, I sigma m, I1, IM from 1 to n.
So the idea belonging to Maxim Kazaryan is to define the weight system GLN for arbitrary permutation of arbitrary number of elements, and which, for the case of Chord diagrams, will reduce to the weight system, to the value of the weight system GLN on this Chord diagram.
Yes, the weight system for the Chord diagram could be a special case for the weight system for permutation. So the GLN of Chord diagram D, and so it's just maybe I'll just show you an example. It says case 3, and then maybe we choose a cut point. This is 1, 2, 3, 4, 5, 6. And this is the summation.
You may just write down the permutation corresponding to this. WGLN of.
So it's 1, 4 times 2, 5 times 3, 6. So it's just a transposition of the two endpoints of the same chord and the product together.
Yeah, so when we take a chord diagram and we pick a cut point on the circle, then we make this chord diagram into a permutation. This permutation is an involution without fixed points on the set of ends of the chord, which is 2 times larger than the set of chords. And we have an involution without fixed points. We know how to define the GLN for a permutation, and we are able to take the value of GLN on this permutation. And of course, the permutation depends generically on the choice of the cut point, but the result is independent of the choice.
And in order to calculate this GRN weight system for permutation, we need another thing called the directed graph. For permutation.
Is it correct that small n in definition of permutation group and capital N in GLN are the same?
There is no small n in the definition of a
No,
permutation. There is small
it's written
m.
that
It's small m, which is arbitrary and has nothing to do with n capital.
then yeah, I'm not able to see the definition of well, can you say again, please, the definition of weight invariant for permutation, because it's impossible to see.
We have a permutation sigma. Yeah, maybe larger letters. No, here it is okay. But
Next line, yeah.
yeah, here. You
So
take
I1,
I1 and
sigma 1.
I sigma of 1. I2
I2, I
and
sigma
I sigma of 2. I
m,
m and I sigma of m.
m is a permutated element
And
of sigma.
the indices I1, I2, Im vary from 1 to
N, capital N.
capital to capital N, yeah. To
and what does it mean to apply to make permutation as sum of capital N?
nope. You take
sigma,
I1 and you take
sigma of 1,
sigma of 1.
Yeah, okay, yeah, sorry, yeah, I understood.
You are not applying the permutation sigma to
okay, so the second index is runs from 1 to m, right?
yeah, the second index runs from 1 to the first index runs from 1 to yeah.
Okay. Whoa.
Диаграммы m маленькое равняется 2n маленькое. 2 количество концов хорда, удвоенное количество хорда.
It's impossible to hear what Maxim said.
For a chord diagram, small m is equal to twice the number of chords. That's the number of ends of chords.
Yes.
And it has nothing to do with the dimension of GLN.
Okay.
Нет, количество индекс I1 меняется от индекс I1 меняется от единицы до n большое. А разных индексов m маленькое.
So the directed graph for the permutation. So we have a permutation sigma, and we write the g of the sigma is a graph have a vertex set is a of the sigma Sm, and g of the sigma is a graph, directed graph, and the vertex set is m, and the edge is I, have direct edge to the sigma I.
Nope. Nope. A permutation which is an involution without fixed points, it determines the chord diagram uniquely. But one and the same chord diagram can admit different presentations as an involution without fixed points.
And so the example, 1, 2, 3. So 1, 2, 3. So it would be look like this. And there would maybe bigger. 1, 2, 3, and you'll have to 1 to 2, 2 to 3, 3 to 1, because there's a permutation of 1, 2, 3, and there maybe another is like a 1, 2, 3, 4. It would look like this: 1, 2, 3, 4. So 1, 2, 2, 1. 3, 4, 4, 3. So this is example of the direct graph for the permutation. And the Casimir invariant.
I'm sorry, I still have question about the previous.
Yeah, you're
So
welcome.
can M be bigger than N capital?
It can be bigger, smaller, or equal. It does not matter. Yeah.
Then if it's bigger, then what does it mean? Say, I don't know, if you're in GL2, what does it mean E1 free? You might have this in
no. I's vary from 1 to N capital. But
right,
indices of Y's. Indices of Y's vary from 1 to M.
Indices. Я не понимаю.
I will reformulate this definition just in the different terms. So we have some number of permuted elements, say 5. 1, 2, 3, 4, and 5. And we have permutations, so we know what's the image of each of the point. 1 goes to 3, say 3 goes to 5, 5 goes to 1, 2 to 4, and 4 to 2. Then we have 5 arrows. We put an index on each of the arrow. I, J, K, L, M. Then for each vertex, there is one incoming arrow and one outgoing arrow. So for each point, I put the E with the indices on the first place I, on the second place K, outgoing. K, J, J, K, J, K. So here I put E, L, M, E, M, L. So here I put E, what is I, K.
Okay.
And
so then you take the, okay. Okay.
I, J, K, L, M, E, I, K, from here, J, K, then this one, E, M, L.
Yeah, thanks. It's it's clear. It's clear now. Yeah, thanks.
So it's clear that for a chord diagram, you just get the original definition. So we have here.
Yeah, it's clear.
May I ask also a stupid question?
Of course.
On this upper right blackboard.
But what are we expected to do if your question will prove not to be stupid?
Okay. It's a definition of my questions. Come on. In this example that still is in the upper right part, where we have the product of these 4 E matrices. Isn't it true that when we take the product of 2 elementary matrices, it's non-zero only when, say, in this product, when J is equal K?
Nope. The question is indeed stupid. You were right. This is the product not of the matrices. EKI and EGI, for example. It's a product of matrix units which are generators of the universal enveloping algebra of GLN.
Okay, so where it's actually acts, that's the question.
It acts nowhere. It does not act at all. It is of course you are able to consider different representations, but of the Lie algebra or of the universal enveloping algebra, which are the same. But these matrices do not act anywhere.
Where?
And you just have generators of an associative algebra, and you have commutation relations between these generators. And the generators may commute, may not commute, but their product is not zero, even if all the four indices are different. If all the four indices are different, you just have two generators that commute with one another.
Okay.
They are not. This is not a matrix product of the matrices.
Well.
Great.
So the Casimir element as the digraph. So CK E I1 I2 I2 I3 IK I1 I1 IK from 1 to n. You can check the definition. It's a weight system of the permutation 1, 2, 3, K. Because this is 1, and this should be sigma 1. Sigma 1 is 2, sigma 1. Sigma 2 is 3. So sigma K is 1. So it's exactly the GRN weight system for the permutation, the cyclic permutation. And the graph is look like 1, 2, 3, K. Like this. And so the goal to calculate the GRN weight system for permutation is to find a way to make the diagram as close as this Casimir diagram, because the cyclic permutation, and we have the following relationship to simplify the diagram.
The idea is that in contrast to the value of the GLN weight system on a chord diagram, the value of a GLN system on a permutation admits a recurrence relation. A recurrence relation which simplifies the permutation and therefore can be applied for computing this GLN weight system. We would like to obtain a result as a polynomial in Casimirs, so the simplification will approach make a permutation closer to a product of Casimirs. You see, in the graph for a Casimir, one does not have intersecting arrows, and the simplification, the recurrence rule, explains what we must do with if two neighboring arrows intersect one another.
So for permutation sigma, and this 2 is the neighboring 2 point. Maybe you call it k or k plus 1. And what you do for the next...
please make the letters larger.
K and k plus 1. This is 2 neighboring point, and you switch the point of this 2 point in the sigma. This is the sigma star, and you leave everything else is still the same, and you just switch the order of the k and k plus 1, and we claim that it's equal to more simplified permutation sigma prime, with there's only 1 point left, and the proof of this rule.
Sorry, don't you need any coefficients on the right?
We call it k prime.
Не нужны коэффициенты, там n не появляется? N не появляется справа? Окей.
Can you repeat the recurrence rule? It is for what?
Sorry, can you repeat the question?
What does mean recurrence rule and how we build it?
Значит, рекуррентное соотношение означает, что мы заменяем вычисление весовой системы GLN на сложные перестановки вычислением на некотором наборе более простых перестановок. Ровно это и означает. Recurrence rule is a way to simplify, to replace computation of the GLN weight system on a complicated the computation on a complicated permutation to computations on a number of simpler ones.
Извини, Сереж, я думаю, что вопрос, что означают эти стрелочки, это ну, как бы наши диаграммы теперь вместо...
Да-да-да, у нас каждой перестановке сопоставлен граф. Вот мы берем граф перестановки и...
Вложенный граф в диске нарисованный.
Ну, насчет вложенный это сильно, потому что там стрелки пересекаются как-то.
Ну да, такой...
Нет,
вот как нарисовано.
Как нарисовано, да. Вот,
с пересекающимися стрелками. И если у нас есть вот такая горизонтальная стрелка, у которой 2 последовательных пересечения, мы можем, ну как бы слева у нас графы, в которых много пересечений, а справа графы, в которых меньше пересечений.
Нет, ну так...
Не, я просто думал, что вопрос про то, что значит...
Ну, хорошо,
да. Справа меньше даже точек.
Справа меньше переставляемых точек. У нас уменьшается... On the right we have a smaller number, permutations of smaller orders, permutations of smaller sets of elements. Because instead of 2 elements, on the right we have 1 element.
So we take graph the same as on the right disk and do such changes.
Yeah.
Вот в этом примере, если мы переставим 2 и 3 местами, то получится 2 независимых цикла. Цикл длины 3 и цикл длины 2. Это было бы произведение Казимиров C3 на C2. А здесь это сложнее, поэтому мы пытаемся поменять местами 2. Эту диаграмму заменяем на диаграмму, в которой точки 2 и 3 поменялись местами, которые мы уже знаем поменять. Но там из-за коммутационных соотношений возникнут дополнительные слагаемые, в которых будут уже инварианты, соответствующие перестановкам на 4 точках. Значит, в левой части та же самая перестановка, ну только сопряженная, то же самое количество элементов, и перестановка такая же, только сопряженная, когда две точки поменялись местами. Сопряжение на транспозицию. А в правой части там меньше количество переставляемых точек.
Okay, let's continue.
So why this rule is correct? So the WGL in of the permutation sigma, it's some term, and in the it's the case place, in this k plus 1 place gets
Larger place.
This is the case place, and here the k plus 1's place, we get EK even larger. Okay. And there has two places. This is a case place. And this is k plus 1's place. We have the E I K I sigma k. And this is E I K plus 1 I sigma k plus 1. And for the second graph, this place is E I K plus 1 I sigma k plus 1 I k I sigma k. Since we just switched the place of these 2 points, and this is the weight system of the sigma prime. And the difference between these two, we only need to focus on these 2 places, which is ik I sigma k minus ik plus 1 I sigma k plus 1. Sorry, not ik plus 1 I sigma k plus 1, and the minus the ik plus 1 I sigma k plus 1 ik I sigma k, which is the bucket of this 2, which is E I k I sigma k with the E I k plus 1 I sigma k plus 1, which equal to delta I sigma k I k plus 1 E I k I sigma k plus 1 minus delta sigma k plus 1 I k E I k plus 1 I sigma k. And for this, we have the we have the I sigma k equal to I k plus 1, which is sigma k. Yes, this is the sigma k, and this is the k plus 1, and these two connected, and the next is the ik sigma k plus 1. So this is k, this is sigma k plus 1, and he connected to the same point. So which means this graph is actually here, and it's the same thing that this is here and there. This is the proof of this relationship, and since we can switch the point equal to have the smaller number of the point, and we can use this again and finally calculate the GL weight system for any permutation. And should I show you an example of how to calculate it by using this?
As Maxim has explained already, the goal is to replace the computation of GL weight system of a permutation with computation of GL weight systems on permutations that are products of subsequent independent cycles.
Yes, yes.
And for such an independent cycle, we just have a Casimir.
Yes.
And so what we obtain is a product of Casimirs.
Mm-hmm. So how many time left? And
So as a consequence, the value of it follows that the value of the invariant of the given permutation is the product of Casimirs corresponding to the length of cycles plus lower order terms.
maybe I speak the symmetric function. Uh-huh. So and I have another approach.
That's the right moment to explain the universality property of, or maybe not explain, but state the universality property that the result is independent of n.
Oh, okay. So the GLN wave system, it's the first of all that if you check the definition that GLN of Chord diagram D is the summation of the EIJ, E maybe KL, something like this, and they just there's a degree is at most 2n because this is
sorry. The universality property is not. You have not yet stated that WGLN of a permutation belongs to the center.
Yes.
Write down this, that please. It's important.
So. So GLN of this sigma, and the sigma is belong to SM, and the sigma have no fixed point. And so this is belong to the center of the universal enveloping algebra. And I say that
you
the
don't
degree
need that sigma does not have fixed points. What is the problem? If you get a fixed point, you obtain just C1, and that's all.
Yes. And the degree of the wave system of sigma is smaller than m, because it's the product is at most m terms, and you sum it together, the degree at most m, which means that the WGLN of sigma is belong to the algebra of the C1, C2, Cm at most, because the Cm plus 1 is not going to be appeared in the WGLN sigma because the degree is fixed. And which means that if n is go to infinite big enough, and the WGLN of sigma is actually a function of the n C1 Cm. So if the n is big enough, so we can actually erase this n, and we call it the GL wave system. For n big enough, the form is not going to be changed. It's only a polynomial about n C1 to Cm to see something which because n is big enough, and for some finite c.
Yeah, there is a natural embedding of the center of the universal enveloping algebra of GLN into the center of a similar universal enveloping algebra for greater values of n. And it happens that our weight system is universal. If you take n large enough, then you obtain a function which depends on n. You obtain a polynomial which depends on n, and C1, Cm, where m is a number of permuted elements.
Yes.
And this value is universal for all n, big enough. Cm. M is a number of permuted elements.
Because the degree is at most m. And the C1 is degree 1, and the Cm is actually degree m. It's not a degree 1 terms.
This polynomial could be applied even if n capital is smaller than m. But if n is smaller than m, then these Casimirs are, have dependence, polynomial dependence. So you could not recognize the polynomial, but if n capital is greater than m, then you can recognize the polynomial.
Okay.
Sorry, what's the problem?
Yeah, here is an example. If we have, in this case, you have permutations of 4 elements, and it happens that the result depends only on C1, C2, and n capital.
And the top order term is C2 squared, which corresponds to 2 cycles.
Yeah,
Yes.
we have C2 squared, and we have indeed 2 cycles, each of length 2. We have no cycles of length 3 or greater.
So do we have time to talk about the symmetric function? And
Yeah.
Okay.
Probably, yeah. Yeah, and this recurrence relation is extremely effective, meaning that a computer program could be written which computes its value on a permutation, and it has been done for permutations with up to 14 elements. So that we know, for example, the value of the GLN weight system on it could be named the GL weight system, since it is universal. And the value of this weight system is known, for example, on the chord diagram with 7 chords, each one intersecting the other one. And also there are computations for chord diagrams whose intersection graph is a complete bipartite graph with many chords.
And next I'm going to talk about another approach to the GL weight system. It's based on this Harish-Chandra projection. So the definition of this projection is, we know that the universal enveloping algebra GLN, you can write it as this way, a minus so H is the EII element, and the a minus is the element.
Try write down, please. Otherwise, H is the commutative subalgebra in UFGLN generated by diagonal matrix units. The Cartan subalgebra of generated by the Cartan subalgebra of GLN. And n minus is a it's not subalgebra subalgebra, yeah, generated by lower triangular matrix units, and if I is smaller than j, this is upper triangular, yeah?
Yes.
Is it probably
Y smaller than Z.
probably we should have I greater как? Окей. Probably. Нет, я понимаю, но lower triangular это те, в которых и больше, чем же. Окей.
And the projection, I call it phi, is UGLN equal to this minus and plus, and then you just project to UH. Just got everything in look like this. For example,
Yeah, the universal enveloping algebra of GLN is non-commutative, while the Cartan subalgebra in GLN is commutative, and therefore its universal enveloping algebra U of H also is commutative. So instead of a non-commutative associative algebra, we deal with a commutative one.
And we know that UH is actually a polynomial algebra of this U11, E22. Yeah. And if we fix this projection on the center of the enveloping algebra of GLN, in which we know that this is a polynomial of the Casimir invariant. And the image is, I call it the lambda star of the n. And I need to give the definition of this lambda star n. Maybe I should give you the symmetric function, shifted symmetric function definition. Shifted symmetric polynomial. So the algebra of and this algebra is, so it's I call this lambda star n. If there's a function belong to lambda star n, and there's n is the number of the variable x1, x2, xn, and after a shift, so shift is x1 x1 xi plus 1 xn, there's a sigma, and you just switch this two places and give a shift x1 xi plus 1 minus 1 xi plus 1 xn and there.
And this is sigma I.
Yeah, this is sigma I.
Sigma I.
And there, after this sigma I, apply to this function. So f sigma I equal to f for any I. So this kind of a polynomial is in the center. It's this kind of polynomial we call the shifted symmetric polynomial. And we have the theorem says it's
this is the Harish-Chandra
fine.
theorem, yeah?
sorry?
Is it the Harish-Chandra theorem?
Yes, isomorphism, yes, Harish-Chandra. JU.
Please write down that it belongs to Harish-Chandra.
Isomorphism. So this projection is from the U GLN to UH. And if you fix on the JUGLN, it's actually give isomorphism. To the
So the Harish-Chandra theorem asserts that when you apply this projection to the universal enveloping algebra of the Cartan subalgebra to an element of the center of the universal enveloping algebra of GLN, then you obtain a shifted symmetric polynomial in the variables E11, E22, ENN. Значит, если вы применяете проекцию вот на второе слагаемое в разложении Harish-Chandra универсальной обертывающей алгебры, алгебры или GLN, то вы получаете и применяете эту проекцию к центральному элементу универсальной обертывающей алгебры. Нас интересуют только такие элементы, потому что все наши эти элементы, они лежат в центре универсальной обертывающей. Все значения весовой системы GLN. То вы попадаете обязательно в алгебру сдвинутых симметрических многочленов от переменных E11, ENN. И эта проекция на центре будет изоморфизмом. This projection, when restricted to the center, is an isomorphism between the center of the universal enveloping algebra GLN and the algebra of shifted symmetric polynomials in the n variables.
Since that the GLN wave system is just lying the center of the universal enveloping algebra of GLN, and we just apply this projection, and then we can find out the shifted symmetric polynomial, which gives us a way to calculate the GLN wave system. For example, we see that the
yeah, and this can be done for the value of GLN on any permutation as well, since it is an element of the center. Значит, в чем состоит идея этой конструкции? У нас проекция Harish-Chandra — это проекция вот этого разложения на второе слагаемое. И если то, что в первом слагаемом, загоняется в ноль. И если мы получаем элемент, который слева делится на элемент из n-, то есть слева там стоит какая-то матричная единица, нижнетреугольная матричная единица, то мы его спокойно отправляем в ноль и про него не думаем. То же самое, если справа стоит верхняя треугольная матричная единица. Мы этот элемент отправляем в ноль и про него не думаем. Остается только... а если у нас слева и справа не стоят... а если у нас есть какие-то не диагональные матричные единицы, то мы пытаемся нижние треугольные перегнать налево, а верхние треугольные направо. В конце концов у нас остаются только мономы от диагональных элементов Е1,1, Е2,2 и так далее. И с ними мы ничего не делаем, они сами лежат в универсальной обертывающей картановской подалке. So if we have what is the idea of the algorithm? If we take an arbitrary monomial in the matrix units Eij, then we just move lower triangular matrix units to the left and upper triangular to the right. And if we have some lower triangular element on the left, we know that this monomial will be projected to 0. And so we can simply forget it.
Yes. So this is an example. C2 is the second Casimir invariant. It's Eij, Eji for Ij equal 1 to n. And it's the center of the universal enveloping algebra. And the phi C2. First is Eii square. And second is Eij, Eji. I is larger than j. The third is I is smaller than j.
And phi is applied to the right-hand side as well.
Yes, yes. And this part is after the projection. It's in the center. It's in the edge, so it's still 1 to n. And this part, Ij, Ji, I is bigger than j, and this is go to 0 because it's I is larger than j in the first. Also, that j is smaller than I in the less than this go to 0. And for this part, it
just write down 0.
0. And plus, also we need a little bit trick about this is using the Lie bucket, which is still phi that Eij, Eji plus Eji, Eij. So we switch the place of these two. Still I smaller than j. So Lie bucket, and the next is switch the place. And this, because I smaller than j, this also map to 0. And so we only have this I square plus, and this it's actually I minus Ejj. So this is I smaller than j, Ei minus Ejj from 1 to n, like this, and we can rewrite it, the result. So now it's already a polynomial of Ei and Ejj, and we know it's shifted symmetric.
Yeah,
and
but one can check
that
it is indeed shifted symmetric.
I Ei minus Ei plus 2 n plus 1 minus I square minus n plus
and
1
n
minus
plus 1 here.
square.
Yeah?
Yes, n plus 1 minus I, and n plus 1 minus I, yes. And so this is the image of the C2. And actually I call it P2, which is base of the symmetric, shifted symmetric polynomial. the shifted symmetric lambda of n, and there we can write it as a of the P1, Pn, and this Pi is the summation of the Pk, Ei minus plus n plus 1 minus I power k minus the n plus 1 minus I power k, I from 1 to n. So this is a case, it's like the summation of the Newton summation. If there's no symmetry, there's no shift, it's just the symmetric polynomial. It's like the Newton power sum, and there seems to have the
yeah, this has the shifted power sums.
Shifted power sum, yes.
Yeah, and in contrast to the previous situation, this computation can be done in for each n separately, and we don't know how to generalize it to a universal. The result is universal, of course,
yeah,
but we don't
the
know.
algorithm is for the specific n. We just apply the projection, and you write it as the polynomial of the pk.
Okay, thanks, Zhuoke. Other more questions, comments? If no, then thanks, and we have a break before the next seminar. 1/4 hour break.